All right, in this worked example, we're looking at a slice of germanium, a cross-sectional area, 1 centimeter squared, carries a current of 56 microamps. The number density of charge carriers in the germanium is 2.0 by 10 to the 13 per cubic centimeter. Each charge carrier has a charge equal to the charge on an electron. What is the average drift velocity? So the equation that should come to mind, and it's actually an equation that's sort of given on the list of formula. It looks like this though. It says electric current I equals A N V Q. So that's sort of the way that it looks on the formula sheet. We kind of think about it like this, or the way we derived it, it's like this. Where the charge carrier in general Q, if it is an electron, well, that's elementary charge E, right? So it could be Q or E. That's why I have sort of both forms of that equation up there. So if you didn't have it memorized, it actually is on the list of formula, right here, the list of formula. This is one. And so we want to make the velocity the subject. So anytime I can, I'd rather sort of make the thing I'm solving for sort of all by itself. And so what would the velocity be equal to in terms of the rest of these? The current I over the number density times the area times the charge E. It tells us the charge is the charge of an electron, so we're safe to just sort of substitute Q for E. Right? Take care of the units that all of our answers are in meters per second, and our distances, right? So the area, length times width is centimeters squared, and the number density is given in per cubic centimeters. Right? So this is how many charge carriers there are in a cubic centimeter, not a cubic meter. Like the unit volume in terms of like the base unit meters, but rather centimeters. So just think about when we go to substitute this in here, the area is going to be centimeters squared. The number density is going to be per cubic centimeters. And so let's actually substitute in all the units as we kind of go through this. I'm going to do the working over on this side. So the current I is going to be the numerator, and it's going to be 56 micro. You have to remember it's 10 to the negative 6. All right. So that's one place where if we're not mindful of what does this little metric prefix stand for, then we get a wrong answer. Right? We have to factor in that there's a 10 to the negative 6 in our numerator. The number density is 2 by 10 to the 13. Now look how I put the units in here. Since that's the number of charge carriers per cubic centimeter, I'm going to move the cubic centimeters up here to the numerator. Right, so it's per cubic centimeter. So like these are the units of this sort of number. But all I care about sort of is what do the units do sort of. So this is the number density per cubic centimeter times the cross-sectional area, 1 centimeter squared. Okay, and then remember that the charge on an electron is 1.6 by 10 to the negative 19, and a coulomb is an amp second. Okay, remember that if I, remember where this came from, I equals Q over T, and then Q is really equal to, you know, NALE, where L is sort of the length of the wire, sort of the length of this slice here. Then an amp of current is a coulomb of charge per second of time. Okay, so a coulomb is really an amp second. So this is an amp times a second. The units, coulombs, are equal to the base units, amp seconds. And so look what I'm going to have here. Amps canceling, these centimeters squared canceling, 2 of those, and I'm left with centimeters per second. It's really important to take care of the units to realize when I crunch these numbers, I'm getting a velocity for sure, but it's in centimeters per second. And it will require one more conversion to give me my final answer. The other thing that you could have done is just converted all of these into meters. You could have said, well, what's 1 centimeter squared in square meters? But then you have really tiny numbers, right? Because a square centimeter is tiny. If you convert it into meters, it's like even tiny, right? So just keep in mind, however you want to solve that, centimeters per second, and then convert it to meters per second, or convert, you know, these dimensions here into meters, and then you get sort of the units in, you get out. All right, let's go have a calculation here. 56 by 10 to the negative 6 divided by 2 by 10 to the 13 divided by 1 divided by 1.6 by 10 to the negative 19. So I get, because then we have it in the calculator and give y'all a chance to practice the calculation too. I'm telling you, students that are like, I've done enough calculations in my life, I don't need to practice this until it's a test. Okay, well, that's a little bit interesting, a little bit risky. Okay, that's up to you. But the students that are always like, hey, I could use the practice, I'm here anyway, you know, you got my calculator and crunch these numbers right along with you. When you make a mistake, you don't get the same answer, it kind of bothers you enough to go, wait a minute, I'm not getting that. It's like, oh, you typed it in this way. Don't do that again. But you'll tend to not make the mistakes when it really counts, right? On the midterm, on the final exam, on the test. So does anyone want to give you a fair chance to calculate? E-learners, you too. Does anybody know what I'm about to write? I'm going to wait until the time shows 9:12, 9:11. I don't know if that's 45 seconds, if it's 2 seconds. I'm just going to wait until this minute expires. Anybody? There you go. 17.5 centimeters per second. Some students that calculate it this way will choose this answer incorrectly, right? I took care of the units. I can see right there, that's centimeters per second. And so if it's 17.5 centimeters per second, I want to set up a conversion where there's 100 centimeters per meter, right? So I'm dividing this by 100 or moving the decimal point over 2 places. So 0.175 meters per second, pretty close to 0.1. In fact, we rounded to significant digits, it would be that. That's why A is the best answer for that.